I'm Derek Pettingale with Discover Energy Systems. Today, we're going to get into a topic around battery management systems, which is one of the key critical elements of any lithium battery. In particular, I'm going to focus on the 48-volt systems out there and how it affects their performance and how things interact on that. The first part is going to be a bit of educational about different aspects of the BMS and explain a few things. And then the second part is going to be a bit more rubber meets the road on how these aspects affect the cost of systems that use these batteries. So we'll be getting into some very specifics around the cost of systems. Great. Okay. So just to reiterate the topic today, selection of lithium energy storage and the impact of the BMS. We know that impacts price. It also affects performance. We'll talk about both today, and we're going to be talking about common 48-volt systems. Perhaps get in the next slide, please. So to make it a little bit clearer, I have a picture here. These are 48-volt systems, Schneider, Solarc. Classic applications for them. So we have a typical off-grid with some MPPT solar charge controllers here. This one I've dumped into a on-grid AC coupled system, a retrofit, very common for home systems out there. We have some typical representative lithium batteries in the 48 volts space on the bottom. And the back end of the presentation, we'll get into very specifics around this. But first, let's get into the background of set the stage for the rest of it. So the first thing that I want to make clear in our category, there's really two types of BMS: a primary, or we used to call them master, but now they're switching over the term primary BMS, and then an onboard BMS. So in this case, the BMS on the battery in the system there, its main job is to govern the current in and out. It's going to be the gateway of current from the batteries to the power conversion electronics, and the gateway from the power electronic devices into the battery. So it has a big influence over that. However, in the 48 volt space, most of what we're using is a BMS per battery rather than one master. The master is master style. The primary style is, there's a few of them out here, but primarily most of the batteries are operating with a single BMS. This allows us to stack batteries together and get more and more current stacked up on there, rather than having to add another master BMS and get into the complexity of that. So two types. We're going to focus on the onboard BMS type. All right, so some of the major elements on board the BMS. The BMS sits on top of the battery cells. It's electronics. It's the home for firmware, or software, some people will call it software firmware, that runs and operates the battery. Its primary function is to ensure that the cells that are beneath it are kept within their operating parameters. They don't go outside that. That's where unsafe things happen out there. So we're looking at keeping the cell in there, so in the safe zone. This is a list of the major items that it's looking after. So first, over temperature. All right, so typically that's somewhere in the 40 to 60 degrees Celsius range. That's a bit based on the particular cells underneath, what they can tolerate. So the BMS is keeping a watch over temperature of the cell block underneath it and governing that. Typically on the low end, it's for lithium is always minus 20 C. Pretty much any battery will discharge that low. Below that, damage will occur, so the BMS will take over. And it should remind you that the BMS, when it is protecting, its main way of protection basically is to disconnect. So this is quite a big difference from lead acid batteries that we were using years ago. They would simply fade away. In this case, there's an actual disconnect moment controlled by the firmware. We can tell you exactly when that's going to happen. And in this case, it would be minus 20 at the low temperature. Over temperature, on charging, again, we're going up to the 40-60 C range, depending on the cell specification on there as well. So those two parameters can vary according to the battery manufacturer and the cells used there. Under temperature, so for lithium iron phosphate batteries in particular, they don't charge below 0 degrees centigrade. We stop. Everyone's going to stop that because damage will occur to those cells if they're charged at temperatures lower than that. So that's kind of a hard stop. Firmware will activate a relay or some sort of control in there and disconnect the battery from the system to protect the cells underneath. Over and under voltage, basically where I'm using 48 volt systems here, but it's 3.65 volts per cell. There's some variations on this for a variety of reasons. And then the other aspect they're looking at is current there. So overcharging of current, so overcurrent and undercurrent, which basically would turn the thing off. So we're going to look at those more specifically because this is impacted a lot by the battery size as much as the cells underneath that. So these are the major aspects: temperature, voltage, and current. That's what your BMS is looking at and acting upon. So some of the key aspects around current. So we're going to look at this. The materials and the construction of the physical materials and construction of the BMS have a large impact on here. Metal is used to carry the current, so there's got to be enough metal in there to carry a certain level of current. So there's physical as well as software control involved here. The ratings for these, there's typically a charge, discharge, and peak power. So if you go pick up a data sheet for a lithium battery, these are three of the key parameters you're going to look for on the data sheet. So how many amps does it take in? That's the charging. How many amps will it let out? The discharging. That's going to affect your inverter charger a great deal. If you can't get enough current out of the battery, the inverter charger can't operate to its specifications. If you can't put enough, or if the charger is larger than the battery, putting the current in there, the charger is going to derate itself to fit the battery. It'll only put the current in that it's allowed to, but then effectively you're underutilizing your inverter charger. You've overpaid for the inverter in theory or underpaid for the battery, one of the two. There is a mismatch there. All right, and then peak power. So short-term durations, bursts of energy, particularly around 48 volt inverters in the off-grid world. That's what's called, they call that surge or peak power on that. So you'll have a look at the data sheet of an inverter charger. You'll often see that they're rated at double their continuous capacity for a short period of time. The batteries underneath them have to be able to go with it, or it can't achieve that specification either. So they have to be able to do a bit of peak surge for a short period of time. So this particular specification, peak power, is always bounded by time. So there should be a rating of a number of seconds on there, how long it will actually be able to sustain that. And that's also, it's determined by the physical characteristics of the BMS, can it carry the current, and what the firmware will allow. These rates, as we call them in the battery industry, we call them C rates. So they're often, the marketing language is like, I've got a 1C battery. Well, what does that mean? That's just telling you the relative amount of current that can go through that particular battery or BMS relative to the capacity. So C rates are relative to capacity. There is a time-bound aspect to them, so a certain period of time. So to put that in, I guess the next slide will give you some examples of that. So it's kind of showing two different BMSs up here, low current, high current. So 1C discharge, 1C charge rate, meaning I can put the full capacity of the battery into the battery in 1 hour, or I could take it out in 1 hour. And in this example up here, we generally would call a low current BMS, it's a half that rate. So in this case, your time's going to double to do the same amount of work. I can put half the amount of half the capacity of the battery in terms of current into it per hour. So it's going to take 2 hours instead of 1 hour. 1C is a 1 hour a number, and a half C would make it 2 hours. If I have 1.5 C, that's 1.5 times capacity. So you're going to take like half an hour to do that. So we tend to use the decimal system. But if you're a lead acid person, you'll recognize those as C/2 and C/3. They're the same thing, just stated a different way. What is probably new, and this will be having an effect on the inverters themselves and the matching of the two pieces together, is the way that UL is interpreting this. All right, so I will recommend that you only use a UL safety certified battery in this case. As I live and breathe every day working with the people that make the rules and test and verify our products, etc., this has become a hot topic. So in the times before now, you used to see on data sheets a lot of max continuous power, 1C, 2C, whatever it is. This is going to start to separate into two. So there's going to be a continuous rate, and under the safety regulations, UL is beginning to define that as 2 back-to-back cycles. So that would be charge, discharge, discharge, fully, 100%. The battery has to be done that under test, and it has to maintain the operation of the battery cells in a safe manner. Typically, that's measured by temperature. The temperature must stay within that. If you can't do that, you can't get 1973. So that's going to become our continuous rate, and we'll probably all have to put those on our data sheets to be accepted by UL. However, that is not necessarily a marketing proposal, shall we say, or the way systems actually get used. There's very, very few inverter systems in the 48 world off-grid or even grid tie that are going to go back to back to back to back at 100% all the time. That's not very often. So a lot of us will be now defining a max rate. What can it do maximum? What's the maximum throughput of that current amount of current through that BMS? And that is going to, you're going to need to see a specific time for that. Otherwise, UL will probably call foul rate on that. So, for example, our company has chosen to put down an hour. So we will put down a max rate, 1 hour rating, and then we'll have a continuous. And the continuous is the rate that we've achieved in our support of our UL application and certification. So that's going to have a big impact the way data sheets are going and the way people are matching products. Of course, if you can't get those numbers, you won't be able to have the inverter do some kind of functions. And we'll look at how this gets applied and what it means in terms of number of batteries on a system and the cost impact of those coming up. But let's move to the next slide. The other aspect of BMS really is about communications, and you will hear in our industry open loop and closed loop all the time. Open loop is simple. It's if you were in the lead, working with lead acid, everything is open loop in there. There is no communication with the battery whatsoever. That's the pure definition of open loop. In those scenarios, you're programming the inverter with the limits that the charger is going to operate and so on and so forth there. So open loop, no communication between the batteries. In closed loop, quite the opposite. The batteries are typically talking across all batteries in parallel, acting together as a single item, going through perhaps translation to get their language to speak the language of the power conversion equipment out there. And you're commuting all that, and they're communicating certain pieces of information. Typically, if it's a CAN communication, they're telling the system what the state of charge is, what the charge voltage should be. This is pretty important. What the current maximum is, a DC current, what that is, and governing all that. Battery temperature, battery fault status if there's a problem. The critical one there really is the charge voltage. So instead of going to your inverter and saying, I want to charge at, 56 volts or whatever it is, and putting that data in there, the BMS, through its communication link, is giving that number All right, so as an installer, that would be like, oh, it's automatic setup. I don't have to do anything. That's their big benefit on that. But this becomes quite important, how this is done and how we can take advantage of that to enhance performance, or how it might restrict the performance of an inverter. So I'm going to talk about some of the advanced aspects of that. We at Discover, we call this dynamic charging or dynamic performance. So in our case, with our batteries, we communicate, we take all the voltages of the various modules that are connected together in parallel, and look at the cells in there, and we do averaging, blah, 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 etc. Do some math, come up with a number. We then send that to the inverter as a target. And CAN bus is high speed, so you can do a lot of calculations. We can reset that. We've spent a lot of time to develop extensive firmware and add that to our BMS, and it will dynamically change that number during the charging process. If you were doing like an RS type communication, not so much bandwidth, more than likely, many of them are just providing a target voltage. They're just programming it instead of having somebody enter the number via the inverter. They're just saying, do this, not necessarily changing the number. You would have to speak to the battery manufacturer to understand whether they do that or not, whether they dynamically change that number or not. But in our case, we do, and it's based on safety considerations. So we're maximizing it, trying to achieve everything in a safe manner. What we're trying to maximize is the voltage that arrives at the battery cells, not what's at the terminal of the inverter. Those two are separate. What matters is what arrives at the battery cell. So in essence, like everybody knows by now that lithium charges faster than lead. And there's a defined pair on there. What we're actually doing is getting close to achieving that full dream. So in this particular chart is an example of how that plays out. One is a open loop system over here. This is closed loop, very same equipment, same batteries, same depth of discharge, same charging equipment on there. Once we close the loop and we use dynamic charging to maximize the arrival of the voltage at the battery pack, we can achieve the ideal fast time. So it appears that it's faster. All we're doing is actually hitting the potential on there, but we do get a faster time. There's a lot of benefit to that, particularly if you're working off grid. I mean, that's a shorter solar day. That's less panels. Or if you're on diesel generator, it's less fuel to get the job done. So this becomes quite important, and it's something that we've worked on quite a bit. I have different graphs for different products. They all work a little bit differently, but in all cases, closed loop is ultimately faster than an open loop. Okay. So that's one of the advantages of open loop, but you'll have to check with the manufacturer whether or not they do a dynamic charging. It's not always possible for me to tell, because I would need to look at their firmware, and that's not always available to me to understand their algorithm. Let's have a look at the next one. So the next aspect that I would draw attention under the dynamic charging category, in this case, is really dynamic balancing. So as the batteries become fuller and fuller, we want them to spend some time out there so that all the cells across all the batteries, etc., can start to level up. No matter what we do or any situation, every cell is going to be slightly different than the next door neighbor. We want to give it the best chance to become all the same. Why do we want them all the same? To achieve the longest life possible, to achieve their life potential. So in our case, with dynamic charging in there, we actually start moving the voltage around, and I've kind of zoomed in on that graph that we had previously here, and this is the dynamic dynamic balancing in course. So we're actually pulling down some voltage, pushing it back up, and moving it like that over a period of time. Why do we want to do that? To prevent an overvoltage fault from occurring. A less sophisticated way is just to hold it there with the voltage, but often that will wind up triggering over voltage and it will shut down before it's even finished the job. So you never really get there. But in our case, we are again using a dynamic algorithm-driven process of leveling that out. And there we're attempting to actually hit the full potential of lifetime, and you know, just that benefit of actually getting the full life of your battery system out there. Okay, so that's sort of the overview. There's a whole bunch of things to do with BMS, as I'm sure everybody will want to talk about those later. I'm happy to do so. If we don't talk about it here, you can come visit with us. We're in 2972 booth, so we're happy to engage in deeper conversations. Now I want to get to the more exciting part. This is where the rubber hits the road. So now we're going to pretend we're an installer and we're buying stuff. We're going to see how this all starts to play out and all of that. So hit that slide up here. All right, so there are 4 dynamics when you're sizing a system, lithium. Required runtime, that's kind of the same thing that we've done for years and years with lead acid. But now we talked about the total charge current, the discharge, and the peak. These 3 become part of the equation that affect the choice of battery and inverter. And we do some quick calculations on those, and we're going to see how that plays out. Can I have the next slide, please? And specifically, I would reuse these examples that I showed up there first. So we have a solar converter, the 15K product, and we're going to use the XW Pro. Both of these are well used, well known, and well established 48 volt products out there. They got specifications on there, but we'll look at them in more detail. I've picked a cross section of batteries. Yes, I'll admit to some bias. I put my own battery up there, our new product. We have some other known competitors out there and listed their specifications. I recommend that you have a look at the slides afterwards. These I pulled the data directly from their data sheets using their specifications on that. And then I went internet shopping and pulled some prices a couple weeks ago. These do change over time, but I went and these are what you could click and buy the products if you wanted to out there. So now we're going to apply these specifications to the 3-4 aspects, the runtime, charge, discharge, and so on, surge. Can I get the next slide? So runtime. I looked at the Solar product and I made a call. I just selected a 2,000 watt load, which is quite a small load, but it serves to our example. 96% divide by that, that's the efficiency of the system to get into a number, times 3 hours. If I do that, I would need 6,200 watts. So you get the next, If you do that and take the specifications of those batteries runtime, divide it, you see that the minimum size to achieve that would be 2 batteries per system, which isn't such a, okay, 2 batteries, no big deal, but if I can have one slide, please. It makes a difference when you see what things actually cost. 2 batteries of each different kind of battery, not exactly the same. All right, so first thing on there, this is where dollar per watt comes in. We talk about it endlessly in my business, and this is where it actually is useful. Can I have peak sizing? A little bit different. So here you're taking the peak output of the inverter, figuring out how much of a DC draw that is needed to support. Divide, you find the peak capability off the inverter, the battery specification, divide in there. And now it tells you the number of batteries that you actually need to make that happen. If you don't have that number of batteries, the inverter can't peak charge. If you're the installer, that's the way you get the phone call in the middle of the night when a pump doesn't start or air conditioning or something is failing and the system goes offline briefly. So that will impact the peak performance on that. We can see that affects system cost size. To achieve that, actually have that happen, it affects the number of batteries, that's the system cost. Now let's take a look at charge and discharging. With the SolARc product, and we're lucky that charge and discharge specifications are exactly the same, which isn't a surprise because it's a bi-directional device. And they got to use the same pipeline to put battery energy into the battery and take it out. So in this case, we know it's a 275 amp charger. Divide that. We look at the rating of charge and discharge from the various batteries and divide that, and we can see that these are the number of batteries there. So required, if we can do that. Of course, impact system cost. Well, so what? What if I ignore this and I just use a few less batteries? Well, in that case, with this product, the charger isn't going to be used to its maximum capability. So you've kind of overpaid for an inverter, something you can't use. And then if you're discharging, well, you can't achieve the 15 kilowatt continuous discharge of that particular product. So you're shortening the capabilities of that product. You're either overpaying for an inverter, go down in size, or get some more batteries to make that happen. So this final sort of slide, you're welcome to download this off the app. These numbers are all in there. So then you can kind of see how this adds up. My pitch to you, of course, my selfishness here, but our battery is able to do that with the least number of batteries in that scenario. So, that's that bottom line. It works very much the same for the Schneider product. There's just some different specifications on that I'm happy to talk about that, but I'm now out of time. Everybody's pushing each along here. So I thank you for your interest on that topic. If you want to go into more details on that or specifics of different scenarios, come and visit me. I'm in booth 2972. Thank you and have a great show, everyone.